And then finally, let me go ahead and start the GitHub desktop. Actually, let's go ahead and immediately start Anaconda. Nope, that's not what I wanted. Hmm. Anaconda doesn't seem to be coming up, so let me start Jupyter Notebook using the terminal instead. All right, so we've finished talking about the basics of Python. We finished talking about NumPy and about numerical analysis, and we've talked a little bit about sound, which means that now, finally, this week, we're ready to really start talking about speech. As I said last week, the next 5 lectures or so, the next 4 lectures now, will be of increasing technical complexity. This week's lecture will be a little bit complex. Next week's lecture will get even more complex, and then even more complex, and then even more complex. That mathematical complexity is to give you just some introduction, just a barely brief introduction to what goes on behind the scenes on APIs for automatic speech recognition and speech synthesis. And then in the last 4 lectures of the course, we'll switch to really talking about those APIs. How can you access automatic speech recognizers and speech synthesizers in order to create your very own dialogue assistant? So today, let's talk about speech synthesis. What I want to do today is to tell you a little bit about what is speech, how is speech created at the voice box, how is it filtered using your mouth, what's the connection between your vocal folds and your tongue and your jaw and your lips in order to create speech. And and then I want to talk a little bit about the math behind those things. So the resonance will introduce the concept of the resonant frequency, and those resonant frequencies for speech are sometimes called the formant frequencies. And so we want to talk about how to synthesize a relatively simple speech sound using those principles. So voiced speech starts out with the vibration of your vocal folds. Your vocal folds are a pair of membranes that stretch across your vocal tract. The original purpose of the vocal folds was actually just to block off your lungs while you're eating. So the idea is that while you're eating, you can block off your trachea so that food doesn't go into your lungs. And sometime in the evolution of our species, sometime before we became human, um, some animals learned how to blow air outward through the vocal folds in order to make them vibrate. And this is all of the mammals that are able to produce sound in the same way. Dogs and cats and all other mammals that can produce it in the same way. Notice that birds produce sound in a different way. Reptiles produce sound in a different way. But all of the mammals that produce sound by blowing air through these vocal folds and making them vibrate. And you can see the vibration of the vocal folds if you put a mirror in the back of your throat, as this person is doing in this old photo from Wikipedia. You can see that the doctor has a light on his forehead, and that light is shining into the mirror on the back of the patient's throat. And the light shines down from the mirror into the throat and then reflects off the vocal folds, and the doctor can look in the mirror to see what's happening in the back of the throat. Right, so that can be done now using a fiber optic scope instead. And so here's an image of a person vocalizing using a fiber optic scope. Let me see, let me expand this. Um, right, so here you can see the vocal folds. So now we're looking down into the throat. The front of the person's neck is at the front here, is at the bottom. The back of the person's neck is at the top of the screen. And you can see that there are these two pieces of tissue, these two almost skin. It's actually a muscle called the vocalis muscle that's opened up now. And these two pieces of tissue will close, and then this person will blow air out through that tissue. We're looking down into her throat from a fiber optic scope. And so what we're going to see is we will see this happening in real time. And all you'll see is that it will close and then it will kind of vibrate a little bit and you won't be able to see anything. And then the camera will use a strobe light in order to slow down the motion. So the strobe light will slow it down so that you can see the vocal folds vibrating back and forth. And then the strobe light will turn off and it will go back to a regular camera again. So let's watch
Here
that.
is a look at some normal young female vocal cords during a stroboscopic exam.
So you can see that it, when it started out, you couldn't really see the vibration, and now it's being slowed. Right now, it's slowed down by the stroboscope so that you can see the vocal folds vibrating back and forth. The vocal folds are vibrating 200 times per second, so you can't see them at their normal rate. When you can see it vibrating, that's because the stroboscope has slowed it down to a rate that we can see. I think you saw that it started out, you couldn't see anything, and then you started to see it. And that was when the strobe light came on in order to slow it down so that you can see what's happening. All right, so that's what's happening inside your throat whenever you speak or whenever you sing. These vocal folds that protect your lungs from getting food inside them, if you blow air out through the vocal folds, they vibrate in this way, producing sound. And that sound can be speech or singing, or it can be a bark or a meow, any such sound. It looks roughly like this. Here's the air coming out through the vocal folds. The vocal folds open and the air increases, and then the vocal folds close and the air suddenly stops. And the air pressure immediately above the vocal folds, the air pressure rises when there's air coming out and falls when the air is decreasing. And it hits a negative spike, and that negative spike then suddenly shuts off because the airflow suddenly shuts off when the vocal folds close. And it turns out that that last spike is the most important part of the excitation. That all of this is fairly gradual. It takes about 1/200th of a second. And that 1/200th of a second is really not a high enough frequency to cause any serious sound. The real sound occurs at this sudden, abrupt cessation of sound. This abrupt stop of sound um, is at a much higher frequency. This drops in less than half of a millisecond, so less than 1/2000th of a second. And that abrupt stop of the sound is at a high enough frequency that it can be heard as speech. And so it turns out actually that it's sufficient to only represent that one pulse, right? It's sufficient to represent speech. You don't need all of this complex waveform. You can make speech intelligible by just representing one pulse. Every time the vocal folds close, you have one pulse of sound, just one pulse. And the key piece of information really is just what is this period? What is the period from one vibration of the vocal folds to the next? That period is T naught samples per pitch period, which is Fs, that's the number of samples per second, divided by F0, which is the number of pitch periods per second. F0 is the pitch frequency. When you sing la, 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 that F0 gives the note, right? So if you're singing, if you can sing a middle A on a piano, F0 would be 440 cycles per second. A typical male speaking voice might be 110 cycles per second. So it might be 2 octaves below the middle A on the piano. And if we sample at 8,000 samples per second, that means that the pitch period is about 73 samples. So once every 73 samples, we should produce an impulse. And the rest of the time, the excitation is just zeros. Right? We've got 1 impulse every 73 samples and zeros the rest of the time. We can produce such a signal by calculating these things. Here's the sampling frequency, 8,000 samples per second. Here's the pitch frequency, 110 hertz. And here's the pitch period. It's Fs over F0, rounded to the nearest integer. Right? Then we'll create the excitation signal, which is just all zeros, 8,000 zeros in a row, 1 second. And then remember this notation. This means that starting at sample number 0, going to the end of the array, once every T naught samples, I want to create a -1. So I just create 1 impulse every 73 samples. Here's the first one at sample 0, the second one at sample 73, the third one at sample 146, the fourth one at sample 219, and so on. So if we create that signal and we plot it, we're plotting the first 300 samples. Note that I'm only plotting the first 300 samples here. Then I can play it back using IPython. And you can hear that it doesn't sound like speech, it just sounds like a buzz, but it sounds like a buzz at a reasonable pitch period, right? It's just exactly that note. But without the speech sound. It only sounds like the buzz. It doesn't have any speech. It's not a vowel in particular, it's just a buzz. So now we've got the vocal folds. Now the rest of the lecture today, I just want to tell you about how we turn that buzz into speech. All right, so far we've got the vocal folds down here at the base of the neck. And now we have to model everything that happens between the vocal folds and the lips. This entire range from the vocal folds to the lips is now what we want to model in order to change that buzz into speech. So to change so here's the vocal folds. The pink on this figure is the vocal folds, right? And that pink region, as you now know, is vibrating 110 times per second for a male, or about 200 times per second for a female, in order to produce that buzz. That buzzing noise then is going to be filtered through the rest of the oral cavity and the nasal cavity if you're producing a nasalized vowel or a nasal consonant. So if you produce or an M or an N or an engma, the sound goes through your nose. If you produce a, e, u, a, o, the sound goes through your mouth, through your oral cavity. In either case, the sound is produced at the vocal folds and it's filtered. We say that it's filtered by the oral cavity. This is exactly the same as a musical instrument. It's actually very much like a clarinet. The reed of the clarinet is the vocal folds. The mouth of the clarinet is the lips of the person. And in between, there's this echo chamber, right? The body of the clarinet, that tube, is like an echo chamber. It builds up echoes inside that echo chamber. And those echoes cause certain frequencies to be enhanced while other frequencies are reduced. All right, so the vocal tract is the pharynx, that's this lower part below the nose, and the mouth, which is the part above the separation of the nose and mouth. So the vocal tract, which is the pharynx and the mouth, is the air cavity between the vocal folds and the lips. That's the lower blue part in the picture above. The nasal tract is the air cavity through the nose. That's the upper blue part. And if you excite air at the vocal folds, you have air coming in right? That air coming in causes an increase in pressure at the vocal folds. So there's not very much air that enters the vocal tract, but there's a huge change in pressure. And that huge change in pressure at the vocal folds causes the atoms of air to accelerate forward. They accelerate forward, but then they reach the lips, which are almost closed, especially if you're saying ooh, ooh, right? The vocal folds are letting very little air through. The lips are letting very little air through. And so in between, the air kind of bounces back and forth. So for ooh, the air is kind of bouncing back and forth in the way shown here. For something like ah, for an ah, it would be as if the air was rushing out. So an ah would be maybe half of this picture, where the air would be rushing out of the lips and then rushing back in through the lips. Very little air is coming through the vocal folds. And so for an ooh, we have something very much like this picture, where the air pressure at the glottis, when the glottis closes, it creates a sudden negative spike of pressure. And that negative spike of pressure causes all the air molecules to rush to the left. And when they rush to the left, they build up pressure, which causes them to rush back to the right again. But when they rush to the right again, they build up pressure against the lips, and so they rush back to the left again. And this bouncing back and forth causes a resonance. It causes a much larger amplitude of sound right at the resonant frequency of this tube. The resonant frequency of this tube is the speed of sound divided by 2 times the length of the tube. So we have the speed of sound, which is 350 meters per second, divided by the length of this tube, which is about 17 centimeters. We wind up with a resonant frequency of about 500 of about 1,000 hertz. So 2 times 17 is 34 centimeters. 350 meters per second divided by 34 centimeters is about 1,000 hertz, which is the resonant frequency shown here for an oo sound. We can model that on a computer using what's called a digital resonator. A digital resonator just has to model this bouncing back and forth. And this bouncing back and forth needs 2 degrees of freedom. We've got the high air pressure that accelerates the air molecules. And then that acceleration of the air molecules builds up high air pressure at the other end. So we have 2 degrees of freedom. And those 2 degrees of freedom are represented by delaying the sound by 1 sample and feeding it back again, and then delaying it by 1 more sample and feeding it back again. And if we set these multipliers, the multiplier B and the multiplier C, correctly, we can model any frequency of resonance. So we take y of n, the output, is the input x of n, plus b times y of n minus 1, plus c times y of n minus 2, where b is e to the negative pi times the bandwidth times the sample period, times the cosine of 2 pi ft, where f is the frequency of the resonance, and bw is the bandwidth. The bandwidth is a concept that the bandwidth means how broad or how narrow is that resonance. Is that resonance something that's just at only one frequency, which we call narrowband, or is that resonance something that's actually covering many different frequencies, which we call a broadband resonance? It turns out to be fairly narrow. This bandwidth will turn out to be a fairly small number, which means that the resonance will keep going for a fairly long time. So we can calculate these coefficients. C is negative e to the minus 2 pi bwt. And in NumPy, raising e to the power of something is used np.exp. exp by default takes e raised to the power of some constant, where e is the base of the natural logarithm. E is an irrational number. It's the number 2.14, 2.7 something. It's a particular number that has some meaning in calculus. If you haven't seen it before, don't worry too much about it. Just know that you can get it by typing np.exponential, and that will calculate this formula: e to the minus 2 times pi times the bandwidth times the sample period, which is 1 over fs. So we take negative e to the minus 2 pi bw over fs, and capital B is 2 times e to the negative pi bw over fs times the cosine of 2 pi times f over fs. And these are just the magic formulas. These particular coefficients then we put into this formula. Y is equal to a times the input, x, plus b times y of n minus 1, plus c times y of n minus 2. And by filtering the sound in that way, by creating the next output sample is equal to the current input sample plus the previous output sample plus the second previous output sample. Those 2 degrees of freedom are enough to create a resonant frequency at any particular resonance. So if I take my excitation, remember the excitation was just a buzz. It sounds like this. And if I create a resonance at 500 hertz, let me specify that, let me define this function, and then let me specify that I want a resonance that has a 500 hertz center frequency and a 100 hertz bandwidth. Then what will happen is I get something that looks like this. You see that in these 70 samples, which is 1/10 of a second, 1/100th of a second, in this 1/100th of a second, it has 1, 2, 3, 4, 5 complete cycles. So this has a frequency of 500 hertz, right? This is 1/100th of a second, and in 1/100th of a second, it has 5 cycles. So it's 500 hertz. And its bandwidth is 100 hertz, which means it decays by about 1/3 in this 1/100th of a second. If we listen to it, let me run IPython here. You can hear it sounds much more speech-like. Rather than just a buzz, now we have something that sounds like it has that resonance. Let's try playing around a little bit with the bandwidth so you can see what this does. First of all, if I make the bandwidth narrower, narrower in frequency will mean longer in time. And you can see that it doesn't decay as quickly in the time domain. And that will give it even more of a tone at 500 hertz. Let's see if we can hear it. Oh, it doesn't sound that different. Let me make it even smaller. Let's make it only a 10 hertz bandwidth and see if that changes how it sounds. Doesn't change very much how it sounds, does it? Let's make the bandwidth much wider. Let's make it a 250 hertz bandwidth. You can see that now it decays much more quickly. Let's see how that changes the sound. Yeah, so if it decays much more quickly, if it has a much wider bandwidth, then that makes it more like the buzz. And the sort of the narrower we make the bandwidth, the less buzzy it is and the more resonant it is. So a narrow bandwidth makes it sound more resonant. All right, so we want it to sound more resonant. We give it this relatively narrow bandwidth, but it still doesn't sound quite like speech. It's getting more speech-like, but it's really not quite speech yet. It sounds more like a musical instrument. In order to make it speech, we need to model all of the other resonances of the vocal tract. So here's some diagrams. These are all from Wikipedia. This is showing the first 4 resonant frequencies of the vocal tract in an oo sound. In an oo sound, actually there's one which is the entire vocal, velocity goes up and down in the entire vocal tract. Here's F1 is sort of the second resonance of an oo sound. And you can see that the air molecules are speeding up and slowing down just in the middle here. Air pressure is building up at either end, at the glottis and also at the lips. The second resonance actually has the air at the back of the vocal tract and the front of the vocal tract are going in opposite directions, right? They compress together and then they go apart and then they compress together. The third formant has the air in 3 different regions of the vocal tract going in opposite directions, like this and like this, right? So you can see that the air, there's a node about 1/3 of the way through the vocal tract and again about 2/3 of the way through the vocal tract. And then the fourth resonance has four different regions where the air speeds up and slows down in four different places in the vocal tract. You can see that there are three different nodes inside the vocal tract, and there's four different regions where the air is speeding up and slowing down in opposite directions. And in order to make it sound like speech, we need to model all four of those. If we don't model it, speech has an infinite number of formants, but the first four are important. The first two determine which vowel it is. The next two make it sound speech-like. In order to make it sound like speech, we need to model all four, and we need to be especially careful about modeling the first two. And we can model all four using this digital filter here. We just take the input E of n, pass it through the resonator at F1, and then pass it again through the resonator at F2, and then again at F3, and then again at F4, where the resonant frequencies and bandwidths for an ah vowel for a male speaker are about 700, 1200, 2500, and 3500. This is just a measurement. These are just measurements for a typical male speaker. A typical male speaker has a pitch of about 100 hertz and has these four formant frequencies at about 700, 1200, 2500, and 3500. So let me start out by taking the excitation and feeding it into the resonator with a formant frequency of 700 and a bandwidth of 100, and I'll take the output and call that Y1. Y1 is this arrow, right? Y1 is the arrow that leads from the F1 resonator to the F2 resonator. And so I'll take Y1 and feed it into the resonator with a frequency of 1200 and a bandwidth of 200. That's the F2 resonator. And the output will be Y2. Y2 is this arrow. Y2 is the arrow that leads from the F2 resonator to the F3 resonator. And then I'll take the output of that, I'll take Y2 and feed it into the resonator again with a formant frequency of 2500 hertz and a bandwidth of 300 hertz. And I'll call the output Y3. Y3 is this arrow. Y3 is the arrow that leads from the F3 resonator to the F4 resonator. And then finally, I feed Y3 into the resonator and give it a formant frequency of 3500 hertz and a bandwidth of 400 hertz. And the result I will call speech. And then let me plot that speech signal. I'll plot just the first 300 samples, and you can see that the first formant is clearly visible, right? You remember this first formant that was the resonance at 500 hertz. That means every 10 milliseconds, it has 5 complete cycles. So you can see that 1, 2, 3, 4, 5. But you can also see some sort of interaction. Here's this weird jiggle here. This weird jiggle is mostly the second formant at 1200 hertz. Right? You can see that this jiggle looks like it might be happening about 10 times in 10 milliseconds. So it's around 1200 hertz. These two higher frequencies, 2500 and 3500, you really don't see them in the time domain at all. The time domain is almost entirely given by F1. F2 is this little jiggle. F3 and F4 are almost invisible in this plot, in the time domain. But we can clearly hear them. This will sound like speech, so let me make sure to synthesize that. I did. So this should now sound like an ah vowel. So you can hear sort of what we've done. We started out with a buzz at the vocal folds. That's the buzz. And then we take that buzz and we filter it with just one resonance. And that's just one resonance just at 500 hertz. It sounds almost like a musical instrument. If we filter it with all four resonances, then we get something that sounds more like an ah. Right? That sounds like ah, 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 something like that. Almost like my voice. All right. So now you know how to create speech. Now we need to talk about how to create speech that sounds like something other than ah. So we've got the basic excitation, that's the buzz. And then we've got these four formant frequencies, these four resonances that make it sound like speech. And now we want to create something other than just the ah. Let's try ah, e, u, a, o. All right. here's a so we create a, e, u, a, and o by moving our lips, our tongue, and our jaw. Right? The lips, the tongue, and the jaw move up and down in order to create speech.
Welcome to the science
Let
gallery
me, this is
of the
not
Max.
shown here, so let me go to the Wikipedia video and show you. This is a lateral MRI of somebody producing speech. Let's watch.
Welcome to the science gallery of the Max Planck Society.
So this is a person, he's lying down in an MRI, and he's saying, welcome to the science gallery of the Max Planck Society. And you can see that as he produces each consonant, his tongue, for a T, his tongue tip, so when he says welcome, for the W, you'll see his lips close. When he says welcome, during the K, you'll see his tongue body will touch the roof of his mouth. When he says M, welcome, the lips will close again. And then for the word to, the tongue tip will touch for the to the, in the tongue tip will touch again. In science, the tongue tip will touch again. And then for the N in science, the tongue tip will touch again. So to the science, you'll see the tongue tip touch 4 times in a row. To the science. And then for gallery, the tongue body will touch again. And then the tongue tip for the L and the R of the Max Planck Institute, and so on. And so you'll see either the lips or the tongue tip or the tongue body will touch for each consonant. In between those consonants, the tongue body moves around. So for the welcome in you'll see the vowel, the tongue is kind of in the middle. For the in welcome, the tongue body will be much lower. So it'll be welcome. The tongue body will be high and then low. So it'll go from touching for the K, it'll go down low to make the in come. And then for to, the tongue body will be higher again. For the, it will be kind of middle again. And then for science, the tongue body will be low and then move up. I, right? So let's see if we can see some of those things. Welcome to the science. It'll happen quite quickly, of course. So let's see if we have time to watch it.
Welcome to the science gallery of the Max Planck Society.
I don't know if you saw it, but science, the tongue went from low to high. As the tongue moves around, it changes the resonant frequencies, right? When the lips are closed, we get an oo sound, which is very much like the resonant frequencies I was showing you before. But when the lips are open, we get a completely different set of resonant frequencies. And those changes determine the vowel. The consonants are more complicated, but the vowel is really entirely determined by F1 and F2. Here are the vowels of, let's see, is this Russian or Swedish? I think these are the vowels of Swedish. Let's see if the Wikipedia page specifies. It doesn't. They had that deleted. Okay, so this is I think these are the vowels of Swedish. You can see E, A, A, O, U, the five Japanese vowels, E, A, A, O, U. And then Swedish also has this vowel A, which also exists in English. This is kind of between A and A, this A sound. And Swedish also has these 3 rounded vowels that don't exist in English. So this is E, this is something like U, this is A, this is something like Ö, and this is O, and this is something, a fronted O, kind of like Ö. I'm probably not pronouncing those exactly correctly because I don't speak Swedish. But let's stick with the 5 Japanese vowels. A, E, U, A, and O. And we can see how to produce them. All we have to do is change F1 and F2 in order to match the frequencies shown here. F1 is at 350 hertz for E and for U. For A and O, F1 is at about 450 hertz, and for A, F1 is 700 hertz. F2 is at about 800 hertz for U, 1000 hertz for O, 1200 hertz for A. For A, it's up here at about 1800 hertz, and for E, it's up here at about 2200 hertz. So we just have to change those frequencies. All of the other frequencies, F3 and F4, don't have to change. It's important that we have F3 and F4 to make it sound like speech, but it doesn't have to change from one vowel to another. Similarly, the bandwidths don't really have to change that much. They're pretty much the same regardless of the vowel. But F1 and F2 really have to change depending on the vowel. And we can create that using a dictionary. Here's a dictionary that specifies that the vowel A has an F1 of 700. The vowel E has F1 of 350. The vowel U has F1 of 350. The vowel A has F1 of 450, and the vowel O has F1 of 500. Similarly for F2, the vowel A has an F2 of 1200. The vowel E has an F2 of 2100, and these are approximate. It could be 2200, that would be about the same. The vowel U has an F2 of about 850, the vowel A has an F2 of about 1900, and the vowel O has an F2 of about 950. These are approximate. This could really be 1000, and it would be just fine. Right, so choosing these formant frequencies approximately, now I can create each of those vowels. Let me create the 5 vowels, A, I, U, A, O. So I'm going to enumerate A, I, U, A, and O. Let me actually print these out while I'm producing them. Let me print now creating the vowel, and I'll specify phoneme. Now, let me say now creating vowel number, and I'll specify the number, which is the phoneme, which is the vowel, and then I'll specify the phoneme. All right, so I'll print out that information so you can see as it's creating each of those vowels. It will create each of those vowels, A, I, U, A, and O, and for each of them, it will pass the excitation into the resonator, and it will use a formant frequency equal to F1 for that phoneme. It'll use a bandwidth of 100 hertz. Then it will take Y1 and pass it again into the resonator. It'll create a formant frequency, which is F2 of that phoneme, and a bandwidth of 200 hertz. Then it will take Y2 and pass it into the resonator with a formant frequency of 2500 and a bandwidth of 300. It will take Y3 and pass it into the resonator and create a formant frequency of 3500 and a bandwidth of 400 hertz. And then the result Y4 will be like a speech signal. So I'll plot the first 300 samples of that speech signal in the subfigure which has that plot number. And I'll set the title to be artificial %s, where %s is the phoneme. So you can see artificial A, artificial E, and so on. And then I will concatenate that vowel to the speech sound. I'll concatenate that vowel, Y4, and after it, I'll concatenate 8,000 samples of silence so that those 5 vowels are each separated by 1 second of silence. So you see it created vowels 0, 1, 2, 3, 4, which were the vowels A, I, U, A, O. And here's the waveform for the artificial A. Here's the waveform for the artificial E. Notice that F1 is much lower, so F1 is this very low frequency resonance. F1 for an E is 250 hertz, I think, 350. So in the 10 milliseconds of one pitch pulse, F1 just goes up and down, up and down, up and down, 3 complete cycles. But now, because F1 is so low, we can really see F2. This really high frequency vibration here is F2, not F1. For the artificial U, both F1 and F2 are very low, so you can see it's very smooth. For the artificial A, it's kind of jagged like the artificial E because it has a very low frequency F1, but a very high frequency F2. And then the artificial O is very smooth like the O. It has low frequency F1 and a low frequency F2. If we listen to all of those vowels in a row, they sound like this. So I think you can hear A, E, U, A, O. In this way, then, we can produce speech that's intelligible. It doesn't yet sound very natural, but you can produce speech that's perfectly intelligible. We haven't covered consonants yet. We've only covered vowels. But using these 5 vowels, you could produce, any sound for which the consonants are not very important. So you could take your favorite utterance. You could say iroha, and you could produce the ioa using these vowels. The homework for this week will be graded using GitHub as normally, and it will basically, you'll produce these 3 functions that are listed in homework 7.py. The first function is voiced excitation. The second function creates the resonator, and the third function synthesizes a vowel by using those 3 resonators. So let's see, let's look at the help for the voiced excitation. The voiced excitation takes as input a duration, which is the length of the excitation in samples, an F0, which is the pitch frequency in hertz, and an Fs, which is the sampling frequency in samples per second. And the result should be a NumPy array, which has a length equal to duration, and excitation is -1 if n is an integer multiple of Fs over F0, and 0 otherwise. So let's create that signal. We want to start out by creating an excitation signal that's duration samples long. We've done that. Now let me change this pass into some real content. Now we've got the excitation sample is 0 samples long, so let's create T0, which is an integer created by rounding off Fs over F0. And then what we want is we want to set every T0 sample, right, starting at 0, going to the end, to -1. That should be all we need. We've figured out what T0 is. It's an integer, which is the closest integer to Fs over F0. And then we set every such sample to -1. Let me go ahead and test that to see if that results in a realistic looking signal. And there we have our buzz. There's the buzz signal that we had with a -1 at the first sample, -1 at the 73rd sample, and again at the 146th sample, and so on. The second function that you should create is the resonator. The resonator takes as input an excitation signal and a resonant frequency and the bandwidth in hertz and the sampling frequency in cycles per second. And it should return the resonant output. All right, for this, we're going to need to go back and look at these magic feedback coefficients. The magic feedback coefficients were -e to the -2 pi bwt. So -e to the -2 pi bwt. Let's write that. So the constant c is equal to negative exponential of -2 times pi times the bandwidth over the sampling frequency. And let's see, the b coefficient was 2 times e to the -pi bwt times the cosine of 2 pi ft. So let's see if we can get that right. B is equal to 2 times e to the -pi times bw times t times the cosine of 2 times pi times the frequency f times the sampling time t. A is equal to 1 minus b minus c. And then we need to set y of 0 is just equal to a times x of 0. We need y of 1 is just equal to a times x of 1 plus b times y of 0, right? And then after that, for n in the range from 2 up to the length of x, we want y of n to equal a times x of n plus b times y of n minus 1 plus c times y of n minus 2. So we're just feeding back the previous 2 samples of y in order to produce the next sample of y, multiplying them by b and by c. Let me just check to make sure I've got the signs right. I want y of n is equal to a times x of n plus b times y of n minus 2 plus c times y of n minus 2. All right, let me check and see if that works. Let me scroll down to the homework, and I want to create a signal, and let's see if it looks like the excitation passed through a 500 hertz resonator. That looks pretty good. All right, and then finally, what we want to do is synthesize a vowel. In order to synthesize a vowel, we're going to take the pitch frequency in hertz, the duration in samples. So we want to create an excitation at this pitch frequency with this sampling frequency, fs. And then we want to pass it through the resonator 4 times in a row with f1 and bw1, with f2 and bw2, and so on. So let's try that out. Let's see, synthesize vowel. Speech is equal to all zeros. Well, that's not really true. Actually, what I want is I want excitation. And that should be this voiced excitation function. I want voiced excitation at the frequency with a duration f0 and fs. Are those the same parameters? Duration f0 and fs, they are. So I can just put duration f0 and fs. And now I want to pass that into the resonator 4 times in a row. Is the resonator just called resonator? It is. So I can take y1 is equal to resonator. And what are the parameters of resonator? X, F, BW, and FS. So the first input is the excitation. The first frequency is F1. The first bandwidth is BW1. And the sampling frequency is FS. Is that right? F, BW, FS. Now I'll take Y2 is the resonator applied to Y1 with frequencies F2, bandwidth BW2, and with the sampling frequency FS. And then repeat. Y3 is equal to the resonator applied to Y2 with a frequency of F3, a bandwidth of BW3, and a sampling frequency FS samples per second. And then finally, the output speech is the resonator applied to an input of Y3 at a resonant frequency of F4 and a resonant bandwidth of BW4 and a sampling frequency of FS. All right, let's save this and see if it produces realistic looking and realistic sounding speech. All right, there's the ah, e, oo, a, and o. And all right, that looks pretty good. Let's try playing one of them. Let me see if I can insert something below here to play ah, e, oo, a, or o. How do I play a sound? I want IPython, right? IPython display audio. And the data will be the most recent speech, which is going to be the O because that was the last one produced, playing at a rate of FS. Let's see if that plays an O. There we go. That's that O signal. All right, that's all we need. Let's just check to make sure that the grading function agrees. And yes, the grading function agrees that those are all the correct methods. So now we can bring up GitHub Desktop. And it says we have 3 changed files, lecture 6 notebook, homework 7, and lecture 7 notebook. So we can write, I did homework 7. Homework 7 is done. And commit those 3 files to my main and then push them to the origin. And once I have pushed them to the origin, they should show up on my GitHub page. Let me go and look. I'm not logged in here, so let me log in. There we go. Now I'm logged in. Let's check to make sure that homework 7 has showed up. There's the excitation, there's the resonator, and there's the vowel. Yep, that all looks correct. So now we can copy the URL and we can go to homework 7 and just paste in the URL. And then once you paste that in, then I'll grade it and you'll get the 10 points. That's all for this week, so let's go ahead and take attendance. Okay, please go ahead and register your attendance using this code. Thank you. And I'll keep this up here for about 2 minutes because that usually is enough time. We have now 4 people who have signed up. We should make this a competition. Maybe I should have a prize to whoever gets the highest, the most rapid response or something like that. I'm not sure what prize to give though. How rapidly can you type in the 5-digit code? All right, we're up to 8 people now, and I think we have 3 more people. Are there 3 more people that want to say that they're here? Up to 9 people. I think we have 2 more people. Are there 2 more people? All right. It's still at 9 people. Is there anybody else who has not yet signed up attendance? Please add your name. Anybody else? All right. Well, I think that's all for today. Thank you, everyone, and I'll see you next week. Have a good week.